Hi everyone. Today we're going to start by talking about the physical properties of diastereomers. So this section of the lecture will help you guys a lot with the lab portion for your post-lab write-up. So when we look at the physical properties of diastereomers, it is known that they have different physical properties. So some physical properties that would be different would be melting point, boiling point, density, solubility, etc. They also will have different spectral data. So something like IR, NMR, mass spec, etc. So what you'll look at in lab this week, you'll look at TLC. So diastereomers will have different RF values. So this is based on differences in polarity. We will also look at GC data. So GC will notice two different peaks. So if you think back, I can't remember if it was lab 4 or 5, you guys analyzed some GC MS data. And remember that your lab instructor told you that this is dependent, the retention time is dependent on boiling points of the compounds. So since diastereomers have different physical properties, boiling point being one of those physical properties, their GC data should show two different peaks. So the differences in physical and spectral data. So this allows us to distinguish the difference between two different diastereomers. So there's a lot of different ways that we can separate diastereomers. So separation can be done. So a few of these you've actually seen in lab already. So the first thing is distillation. So distillation is something that you have not seen. Distillation, what you do, this is based on differences in boiling points. So what happens is you have some heating source, so say like a sand bath. You have your flask here with your mixture of your diastereomers, and then you will have some condenser. So remember condenser, we have water in, water out. And then you'll have a receiving flask over here. So again, you can alter the temperature of the sand bath and you can collect in your receiving flask the diastereomer with the lower boiling point first, and then disconnect that flask, and then you can attach a new flask and collect the diastereomer with a higher boiling point. So another means of separation is recrystallization. So recrystallization is something that you guys did actually in lab 1. So when you synthesized Tylenol, you crystallized it with, I think it was water that you guys used. And this is based on the differences in solubility. So things that were impure would stay in the solution, and things that we wanted to crystallize out would not be as soluble in the solvent that you use. So again, recrystallization is dependent on differences in solubility. So another means of separation is chromatography. So chromatography you guys also did in lab. So column chromatography, you looked at acetylferrocene and ferrocene. And this again will be caused by differences in solubility or even polarity of your compounds or your diastereomers that you're separating. So physical, let's look at enantiomers. So with enantiomers, you will see in lab this week that they have identical physical properties. So that means that we cannot see a difference in boiling points, melting points, density, solubility. So that also means that based on TLC, we should not see any separation. They should have the same RF value because they have the same polarity. On GC, we should only see one peak for both enantiomers because, again, they would have the same boiling points. Another thing with enantiomers, they're also going to have identical spectral data. So since it has identical spectral data, something like IR, NMR, mass spec, it would look the same for both enantiomers. So the only difference with enantiomers is that they can be distinguished by the way that they rotate plane polarized light. And this is called optical activity. So there are different ways that enantiomers can be separated. So we're not actually going to really get into this part. So this is kind of a part that we're going to skip. I'm just going to briefly mention the ways that they can be separated. So we can use chemical resolution. And we can also use chiral chromatography. So this part is in the notes. If you guys are interested, you can look over this, but again, you will not be tested on this part. So let's kind of get back to the optical activity part. So the optical activity part, we can, sorry, I'm just trying to move this down. So analysis of enantiomers with polarimetry. So again, this is going to help us analyze our enantiomers by optical activity. So what polarimetry is this is used to measure the direction and the degree to which plane polarized light is rotated. So the way that we do this is we use a polarimeter. So again, this is what is measuring the rotation of the polarized light. So compounds with the same formula that rotate light differently are going to be called optical isomers. So this figure right here is a scheme of a polarimeter. So sodium light is our source. This is commonly used as a source for a polarimeter. So the light originates at the source, and it's going to pass through the polarizing filter, which is shown here, and the sample cell. So an optically active solution is going to rotate the plane of the polarized light. So it's going to turn until a max of light is observed, and then the rotation would be read out. So the specific rotation, let's look at a formula for specific rotation. So specific rotation can be looked at by this formula here, and this is going to equal the specific rotation at the sodium D line at 25 degrees Celsius. So the sodium D line, what this really means is that the D line of the sodium spectrum, so this is really between wavelength of 589 to 589.6 nanometers. So this is going to be our observed rotation of a sample. C is going to be your concentration, so this is going to be shown in grams per milliliter. And then we have path length. So path length is going to be in decimeter. And just a side note, 1 decimeter is equal to 10 centimeters. So we have different directions of rotation, which if you started the lab, you will see this. And this is how the post-lab questions are kind of formulated, what they're formulated around. So if we have a positive rotation, or this can also be looked at as a clockwise rotation, this is called dextrorotary, or it's just shown with little d is the most common. We also have negative or counterclockwise, and this is called levorotary, and this is shown with little l. So you guys are looking at D carvone and L carvone as your enantiomers in your lab experiment this week. So this is important. Enantiomers rotate light in equal magnitude but opposite direction. Whereas something that is a diastereomer, since diastereomers have different physical properties, there's no way to really predict the specific rotation of one diastereomer if you're given the specific rotation of a certain diastereomer. So let's look at your carvones. So we have so here's our stereocenter. This would be our carvone. This will be good practice if you want to practice your stereocenters of R and S configurations. So this is S carvone. So when we look at some physical properties, so boiling point for both of these is going to be 231 degrees Celsius, which we would expect because, again, the physical properties are going to be the same. So if we look at the specific rotation, again, this is going to be the sodium line, the D line, at 20 degrees Celsius. So our carvone is going to be minus 62 degrees, and the S carvone is going to be positive 62 degrees. So in terms of optical isomer nomenclature, there's a few ways that this can be written. So our carvone can be called, you can see it written as minus, which is indicating it's the negative rotation. So negative carvone, or more commonly, I would say you'll see it written as L carvone, whereas S carvone can be called plus carvone, again, just indicating it's moving it in the clockwise or positive direction, or D carvone, which again is more commonly written. So this is important. R and S do not correlate with the positive or negative direction that it's rotating light. So don't just think that because it's R, it's always going to be negative. Because remember, R and S configurations are dependent on the spatial arrangement of those atoms. So let's look at the analysis of some optically active mixtures. So I put a question on your homework set because it's open book that you can practice enantiomeric excess, but you won't be tested on this on the quiz. So we're not really going in depth with this. I'm just going to give you guys kind of a brief overview of what enantiomeric excess really means. So sometimes as a chemist, we deal with mixtures. Well, most times I would say we actually deal with mixtures. So these can neither be optically pure nor racemic. So racemic is a new word that you may have not heard. So racemic means that we have enantiomers in a 1-to-1 ratio. So again, equal amounts of each enantiomer. So when we have equal amounts of each enantiomer, which we'll get into this on the next lecture, but these are not optically active. And the reason for that is because the rotational effect of each enantiomer would cancel each other out. So for the carbones, if you had, for example, a racemic mixture, that would be a 1-to-1. So we would have something rotating in the minus 62 degrees and then the positive 62 degrees. So if it's a racemic mixture, that would mean that these two values here are just going to cancel out. So we would say that it's not optically active. So when we're looking at something, when we have, so in the cases of something is not optically pure. Sorry, that shouldn't say sometimes, that should say something. We call this, we can calculate the optical purity, which is shown by OP, or the enantiomeric excess, which is shown by EE. So the formula for this optical purity or enantiomeric excess, these are equal. So this is going to be the specific rotation of a sample divided by the specific rotation of the pure enantiomer, which is, you can find on like PubChem or any of the scientific websites. And then you would just multiply this by 100%. So this would give us our optical purity or our enantiomeric excess. So let's look at an example. So if we have a 10-gram sample and it has a specific rotation at 25 degrees on the sodium D line of minus 29 degrees, and we want to know what is the optical purity of this phenylalanine, we know that the pure specific rotation, again by looking this up, is equal to minus 34 degrees. So for the optical purity, what we would do is we would just take our minus 29, which is what we experimentally observed, and we would divide this by the specific rotation of the rotation of the pure enantiomer. Again, just looking it up on PubChem. And then you'll multiply this by 100%. So we would have 85% enantiomeric excess for this specific compound. So again, this material on optical purity or enantiomeric excess, there is a question on the homework set, but again, you will not be quizzed on this for chapter 5. So review all the notes on the physical properties. This again will help you a lot with the write-up for your lab. And if you have any questions, don't hesitate to reach out to me. Have a great day, everyone.